Hello students, welcome. So today we want to proceed to question number 3 of chemistry paper 2, and the question will be from the electrochemistry part. Kindly stay with us until the end of the video. So question 3, Roman 1, we are told study the standard electrode potentials given below and answer the questions that follow. Part A, with a reason, identify the strongest Roman 1 reducing agent. So when we're asked about the strongest reducing agent, we have to look for the one that's having the most negative. So the ones that are having negative are 2, the first 2, then that means the first one is having the most negative. So we are going to take D as our answer. So we're going to put D there. We are told give a reason. So we can give several answers. One, we can say it has the most negative standard electrode potential values. That's number 1. Second reason, we can say because it has the highest tendency to lose electrons. That's the second reason. Then the third reason, we can say it has the lowest tendency to accept or to gain electrons. Those are some of the reasons we can give out. So Roman 2, the oxidizing agents. We are supposed to identify the strongest oxidizing agent. When we ask about the strongest oxidizing agent, we have to check the most positive. So the ones that are having positive are these two, and this one is the one that's having the most positive. Although they have not shown the positive, but we can see 2.87 is a positive value. So we are going to say R. So the answer is R. We are supposed to give a reason. We are supposed to give a reason. We can give again some reason, like the first one we can say because it has the most positive standard electrode potential value. That's the first reason that we can say. Second reason, we can say it has the highest tendency to accept electrons or to gain electrons. Then thirdly, we can say it has the lowest tendency to lose or to donate electrons. So let's proceed to part B. We are told calculate the EMF of a cell made of G and M. Let's take G and also M. G is here. It is having negative 2.36. What about M? M is having positive 0.34. So if you want to calculate EMF, we can use several formulas. The first formula is we are going to use E reduction minus E oxidation. That is the first formula that we can use. So here, E reduction, substance that undergo reduction is the oxidizing agent. So in our case, the oxidizing agent is the one that's having the positive value. So there, we're having positive 0.34 volts minus. Then the one that undergoes oxidation is the reducing agent, and the reducing agent is the one that's having the negative. So here we're having negative 2.36 volts. So when we put this one in the calculator, what we are going to get here will be having positive. Then we are going to have 2.70 volts. That will be our answer. But B, we are saying the standard electrode potential value of a cell is given by the standard electrode potential value for reduction and minus that of oxidation. So it will be positive 0.34 plus minus 2.36. What we are going to get is positive 2.7 volts. So let's proceed to part C. So in part C, we are told write the cell representation for the above cell in B. So when we are writing cell representation or cell notation or cell diagram, what we are supposed to start is first of all the most reducing agent. So in our case, the reducing agent between G and M, it was G. So we're going to have there G solid, then slash. That's the phase boundary. Then we are going to have G2 plus aqueous. Then next we are going to have the solid bridge, that is the vertical line. Then we are going to have the M, that's the one that undergoes reduction or the oxidizing agent in solution form. Then we are going to have the phase boundary. Then we are going to have that substance in solid form. Then we are going to put the standard electrode potential value for this cell, and we have gotten here positive 2.7 volts. That's how we're going to write our cell representation or cell diagram. So here we are having part C, write the cell representation for the above cell in B. It's the way we have said. Then part D, we are to draw a cell diagram for the cell in B above. So these are the two beakers that we are talking about. Then we are going to have the solution of the G ion and the rod for that G, or the electrode. So we can write G electrode or G rod. On this other side, we are having the other beaker containing solution containing M2 ions, and the rod dipped into that solution is M rod or M electrode. Then the two electrodes are connected using a metallic wire, and the two solutions are connected using a salt bridge, and we are taking potassium nitrate as our substance that's in the salt bridge. So part E, we are told write the cell reaction for the drawn cell diagram in D above. So when we are writing the cell reaction, first of all we start here, G solid. Then next we are going to write M2 plus aqueous. Then what will happen is displacement reaction will occur. Then we are going to write G2 plus aqueous. Then we are going to end with the M solid. That is the cell reaction. So let's proceed to the next part. So let's proceed Roman 2 of our question number 3. We are told electrolysis of aqueous solution of metal M resulted in the deposition of 1.07 gram of metal upon passage of a current of 1.32 amperes for 75 minutes. Then in bracket we are given the relative atomic mass of M, that's 52, and we are told 1 Faraday is equal to 96,500 coulombs. So part A, we are to calculate the quantity of electricity passed through the cell. What was the formula for calculating quantity? It was IT, where I is current in form of amperes and T is time, which must be in seconds. So here, what we are supposed to say is we are going to have 1.32 multiplied by the time 75 minutes. But we have to convert it into seconds by multiplying 60. What we have gotten there, or what we are going to get there, will be the quantity of electricity passed. So let's check. But Roman B, we are told calculate the charge on the metal ion. So 3 marks. Let's check the calculations. I'm going to explain on the other side. So in part A, we said quantity of electricity, which is Q, is given by AT. I is current, so we're given 1.32 as our current. Then the time here is 75 minutes. We have to multiply by 6 to convert it into seconds. So when we put it in the calculator, what we are going to get is 5,940 coulombs as our quantity of electricity passed. Part B. In part B, we are asked to look for the charge. So we say N is equal to Q, that's the quantity of electricity passed, multiplied by relative atomic mass. In our case, we are given 52, divided by M. M is the mass. We are given 1.07 times F, that's 1F is equal to 96,500 coulombs. So let's put it. So we're going to have 5,940, which is for the quantity of electricity passed, multiplied by the RAM, in our case 52, we are going to divide by the mass deposited, that's 1.07 times Faraday, that's 96,500 coulombs. Here we are going to get 2.99 Faradays. So that will be the charge, and the charge must be a whole number, so we have to round off. We are going to get 3, so we are going to say plus 3. Learners, that's the end of our class for today. Thank you for watching.